The ideal gas law relates pressure, volume, and temperature for a gas. Our equation for the ideal gas law is PV equals nRT. P is for pressure, which can be in any of our pressure units, atmospheres, millimeters of mercury, torr, or kilopascals. V is for volume. Our volume has to be in liters so that it will cancel out with our R value. N stands for number of moles of gas. T stands for temperature, which has to be in Kelvin. And R is the combined proportionality constant called the universal gas constant. And we can actually solve for it. So let's say that we have 1 mole of a gas at STP. Well, we have all the information that we need in order to calculate R using PV equals nRT. So we have PV equals nRT. And let's use atmospheres for our units for pressure. So standard pressure in atmospheres is 1 atm. If we have 1 mole of a gas at STP, the volume is a constant, and that number is 22.4 liters. For N, we'll plug in 1 mole. We're going to calculate R, and standard temperature is 273 Kelvin. So we have 1 mole of a gas at STP. When we solve for R, we're going to get 0.0821. Now we're going to have a pretty complicated unit for R. ATM liter per mole Kelvin. Now the R value is pressure dependent. So as long as our pressure is in atmospheres, our R value will be 0.0821. The R value will be different if our pressure units are different. So we'll make a little table up here. Let's put the pressure units and the R value. If the pressure units are in ATM, we just solved for R. So 0.0821 ATM liter per mole Kelvin. If our R value is in millimeters of mercury or torr, we would get a different R value. We would get 62.4, and our units are slightly different. This time it would be millimeters of mercury liters per mole Kelvin. Those are the two most common R values. We might also see pressure in kilopascals, although this is the least likely out of the three. And if our pressure is in kilopascals, our R value is going to be 8.31 kilopascal liter per mole Kelvin. So when we look at the PV equals nRT equation, we can solve for any of the variables as long as we're given 4 out of the 5. So our ideal gas law states that gases behave as ideal in an ideal gas law equation, and it works best at high temperatures and low pressures. And we'll talk a little bit about that later. Let's look at a problem. Let's say that a 5.0 liter flask contains 0.60 grams of oxygen at a temperature of 22 degrees Celsius. What is the pressure, and it specifies in ATM, inside the flask? Well, anytime you see a problem that talks about volume, temperature, and pressure, and it doesn't give you changes in those values, you're looking at an ideal gas law problem. So we'll put down our equation. PV equals nRT. And we'll plug in our variables. So for pressure, we're trying to find that. So we'll put in P. Our volume is in liters, so we don't have to do any converting with that. We'll plug in 5.0 liters. Now we've got a problem with N, because N stands for the number of moles of gas, and that's not what we're given. We're given grams of gas. So we're going to have to do a conversion first. So we'll do that down here. We've got 0.60 grams of oxygen, and we know that 32.00 grams of oxygen per mole of oxygen. So that'll give us 0.019 moles of oxygen. Now we can plug that in. So 0.019 moles. Since we want pressure in atmospheres, we'll use the atmosphere R value, which is 0.0821 atm liter per mole Kelvin. And our temperature we need to convert to Kelvin, so we'll add 273 to 22, and that'll give us 295 Kelvin. Now we're going to divide both sides by 5.0 liters, and that will give us our pressure. So pressure will equal 0.093 atm. And when we look at the units up here, our moles cancel out, our Kelvin cancels out. We're dividing by liters, so liters cancels out, and that leaves us with atm. So we know we have our problem set up right. Here's another problem. How many moles of a gas at 104 degrees Celsius would occupy a volume of 6.8 liters at a pressure of 270 millimeters of mercury? So we've got number of moles, a temperature, a pressure, and a volume. So we've got PV equals nRT. We'll plug in for P, 270 millimeters of mercury. For V, 6.8 liters. We're trying to find the number of moles of gas, so we'll plug in N. We're going to need to use the R value that matches up with millimeters of mercury, and that's 62.4. And that's one reason why you want to always write out the units for your R value so you can double check that they match up. And then we need to add 273 to 104 to get our temperature in Kelvin, and that'll give us 377 Kelvin. We're going to divide both sides by 62.4, divide both sides by 377, and that will isolate our number of moles. So we get 0.078 moles of this gas. Now, if the question had told us what the gas was, we could also then do a mole conversion and figure out how many grams that is. Now we're going to relate our ideal gas law problem with stoichiometry problems. And when we do this, the problems are going to have the same type of solving strategy. We always want to take whatever information we're given and convert it to moles, so that then we can relate the moles of reactants to the moles of products. But this time we'll use PV equals nRT in order for us to solve for moles. So let's look at a problem. And this is a fairly long problem, so we'll read out the problem and pick out the variables, and then we'll solve it on the next slide. So it says a gas sample of methane having a volume of 2.80 liters at 25 degrees Celsius and 1.65 atm was mixed with a sample of oxygen gas having a volume of 35.0 liters and 31 degrees Celsius at 1.25 atmospheres. The mixture is ignited to form carbon dioxide and water. Calculate the volume of the water vapor formed at a pressure of 2.50 atmospheres and a temperature of 125 degrees Celsius. So we're starting out with methane and oxygen. We're producing carbon dioxide and water, so we're looking at a combustion reaction. We're going to have to write and balance the equation and then solve our problem. So methane is H4. We're going to react it with oxygen. We're going to produce carbon dioxide and water. We want to balance the equation. 1 carbon, 4 hydrogens, 2 hydrogens. So that'll balance out our hydrogens. 2 plus 2 oxygens, that gives us 4. So 2 times 2 gives us 4 oxygens. Now let's write down the numbers that were in the problem. So we had 2.80 liters, 25 degrees Celsius, and 1.65 ATM. And for oxygen, 35.0 liters, 31 degrees Celsius, and 1.25 atmospheres. And we're ultimately trying to find the volume of this gas that's produced. So we have a limiting reactant problem, and we're going to have to figure out which is our limiting reactant. So let's do moles of methane. PV equals nRT. So our pressure is 1.65 ATM. Our volume is 2.8 liters. We're going to find out how many moles. We'll use our R value that matches up with our pressure. And we'll change our temperature to Kelvin. And when we solve for N, we get 0.19 moles. We'll do the same thing for oxygen. PV equals nRT. So this time we've got 1.25 ATM, 35.0 liters. How many moles? 0.0821 ATM liter per mole Kelvin. And we'll add 273 to 31 to get Kelvin. So 304 Kelvin. When we solve for N, N will equal 1.8 moles. Now we need to figure out what our limiting reactant is. And the balanced equation tells us it's a 1:2 ratio. So we're going to divide the moles of methane by 1 and the moles of oxygen by 2, and the one that gives us the smaller number is the limiting reactant. So our limiting reactant is methane. Now we can do a stoichiometry problem. 0.19 moles of methane. The balanced equation tells us for every 1 mole of methane, we need 2 moles of water. So that'll give us 0.38 moles of water. Now we can figure out the volume. PV equals nRT. The problem tells us that our new pressure is 2.50 ATM. We want to find our volume. The moles are 0.38. Our R value will be 0.0821. And our temperature is 398. Okay, so we can solve for our volume by dividing both sides by 2.50, and we're going to get 5.0 liters of water vapor. And that's how we connect the ideal gas law equation with stoichiometry.